Greetings, fellow freethinkers. The event you're about to watch was hosted by the Centre for Inquiry Ontario, an educational and outreach organization dedicated to promoting and defending science, reason, and free inquiry in every area of human endeavor. My name is Justin Trottier, and as Executive Director of CFI Ontario, I would like to take a minute to tell you about us. Our centre, located in the heart of downtown Toronto, is the first Canadian branch of CFI and is our nation's first dedicated meeting and event space for humanists and freethinkers. Our mandate encompasses a robust public education presentation series throughout Ontario, campus outreach as we support a growing network of student freethought groups, community outreach and social services to provide humanistic alternatives to religiously monopolized services and activities, and a lending library and media center that, among other things, broadcasts videos like this across the planet. To learn more, please visit us at cfiontario.org. To get on our email list or to learn how you can support our movement or get a freethought group started at your campus, simply contact us today at info@cfiontario.org. Thank you for your time, and I hope you enjoy the video. Great. So thank you for coming to the opening event for the first anniversary celebration series of the Centre for Inquiry Ontario. I'm thrilled to see all of you. If you don't know me, I'm Justin Trottier. I'm the director at CFI. I want to first thank everybody who's helped to make this year such a great and successful first year for us. All of our volunteers and all of the committee leaders, so you know who you are. We just do a quick round of applause for the countless dozens of people. Thank you. We do have a whole week's worth of activities. I will describe those in a bit, but first I'd like to play a short video. If those of you who were at our inaugural event on March 10th of last year may remember Dr. Robert Buckman giving one of the keynote addresses and doing the toast, hosting the toast portion of that evening. And I think it's appropriate that he says a few words, very short, to sort of as a celebratory opening set of remarks. So, could you please play it?
I just want to say happy birthday. This first birthday party for the Toronto CFI is a very, very big deal indeed, because over the last many thousands of years, organized religions have bought into a sense of community. They've bound together religio, people, with a sense of community. And I have to say that people who don't believe in the supernatural and don't believe in gods or God actually haven't really had a great sense of community until relatively recently. And the whole CFI, the Centre for Inquiry movement, and Paul Kurtz starting it, has been a brilliant, brilliant step forward, partly because it established basically a community of communities. Now in Canada there are about 18%, I gather, of people who say that they don't believe in God. And now, thanks to the CFI and similar places, there are places for those people to go and actually know that there'll be amid and among people who basically feel the same. And that sense of community has been lacking so far, and that's why the CFI is really an important advance. So it is very genuinely that I say, happy birthday, CFI.
Okay. Well. Dr. Buckman has always been a great supporter of ours. Just a few brief words. The rest of the week will consist of a meeting tomorrow, very important sort of AGM for all the groups involved in this, which is completely open to the public, so I urge all of you to join us from 1 to 4. Then we'll be having a party with a number of activities, including we will be honoring Earth Hour from 8 to 9 with candlelights, etc. Some interesting activities will ensue. That's tomorrow as well from 4 to 9. And then we'll be closing, we have a series of other things which you can check on the website. And then we'll be closing with a talk by Tom Flynn the following Friday, next Friday that is, from 7 to 9. Tom Flynn will be here. He'll be talking about his new Encyclopedia of Unbelief. Tom Flynn is the editor of Free Inquiry magazine, one of the flagship publications of Centre for Inquiry Transnational. So he'll be talking a bit about this new Encyclopedia of Unbelief, covering in particular the history of the free thought movement in Canada. You may not even know that there was one. Actually, there was quite a vibrant one for the last couple hundred years, and he'll be sharing some of his insights on that. If you support what we do, and if you agree with Dr. Buckman that CFI is providing a much-needed sense of community, we do these educational events, the Voices of Reason series, we have our social services, ESL, free ESL service, so coping without religion support group, secular sobriety support group. Many of you already know about these. If you do support all of these initiatives, political advocacy, etc., the campus outreach, then do become a friend of the center. I know probably about half to two-thirds of you already are, but those of you who aren't, please join us. If you're a student, it's as low as $20 a year. The general admission is $60. Now, if you add up the cost of all these events that we have every 2 weeks, actually every week we have something, it's about a $300 value. So we think it's quite a good deal for you. And we will reimburse you today's, or put today's admission towards that friend of the center cost. So do keep that in mind. Now, I'll tell you a bit more about the rest of the activities this week and a little bit, some other exciting news during the intermission, which we'll do after Dr. Peet does her talk. So let me introduce Professor Amanda Peet, and we'll go from there. Some of you may have already seen Dr. Amanda Peet. She was featured in The Elegant Universe, which was a PBS documentary a few years back. We actually have it here, so if those of you are interested in getting more information about string theory, you may want to view it. Amanda Peet is an associate professor in the physics department at the University of Toronto. She grew up in New Zealand, where she went to school and earned her undergraduate degree at the University of Canterbury. After earning her PhD at Stanford and taking up postdoctoral research positions at Princeton University and the Kavli Institute for Theoretical Physics at UC Santa Barbara, she was hired at the University of Toronto in the Department of Physics in 2000. She currently holds the rank of associate professor. Her awards have included an Ontario PREA Award, a fellowship of the Radcliffe Institute for Advanced Study at Harvard University, and an Alfred P. Sloan Foundation Research Fellowship. She counts physics education and outreach among her passions, and as you'll see, she's quite a whiz at these sort of public science engagements, having done dozens and dozens of them, I'm sure. Without further ado, I'd like you to welcome, assuming she's ready, Professor Amanda Peet.
Not working with the display, so while we work on it, you'll have to figure something out, because nothing's happening here at the moment. So I can't proceed until, would you like to please get
So if you don't know, CFI, one of the main things that we do is campus outreach. We have about 23 and growing campus-affiliated free thought, atheist, skeptic, humanist groups all across the country, 23 and counting. They range from groups in Victoria, BC, all the way to Montreal. Unfortunately, nothing in the Maritimes right now. They've actually been getting a lot of press attention, and I don't often get a chance to plug that, and we don't all know about it because CFI is only here in Toronto, but this would be a good opportunity, since this is very awkward and I have nothing else to talk about, to share with you some of the press that we've been getting elsewhere in the country. John, I think, is actually in the hall, but he's brought some friends. They're from the York University. If you don't know, York University got national press attention. Their student group there, free thinkers, atheists, and skeptics at York, in the last month, when there was a big abortion debate that they were to take part in. They were to represent the pro-choice side, and the student union took it upon themselves to cancel this event at the last minute. It became a big free speech issue. In any case, they ended up getting attention in the Toronto Star, CBC Radio, God, I hope that's about to work, in other places. And we're very pleased that that happened. So that's York University. All of this, by the way, is on the CFI Ontario site, so if you'd like to see what I'm talking about, you're quite welcome to visit that. Are we good? I'll tell you more now. Okay, I'll tell you more about it now. We also got press attention at Wilfrid Laurier. We have a Laurier Free Thought Alliance group there. They were actually denied ratification for their group for a number of reasons, including a little bit in their constitution. I may have told you about this at last event, in which it said that you could be moral and content with life without believing in God. This was seen as very, very aggressive. And so they were denied ratification. This became a huge issue on the blogosphere, as you can imagine. Atheists tend to rule the blogosphere, it seems. And it got so much attention that they actually caved within 2 days. They had an emergency meeting, and the group got ratified. They've had several events since then, so it's been quite a success story. Thank you. Go on and on. We've also had a lot of attention at Guelph University, Guelph Campus Skeptics. Guelph University has had 3 events this month with 250 people attending in total. They've had attention in the Guelph Mercury, the local paper. They've had some national attention as well. We've had a number of events on evolution and just science and the education curriculum and all that sort of thing. In Alberta, our University of Alberta atheists and agnostics at the University of Alberta in Edmonton were in the Edmonton Journal. They were in CBC. There was a feature piece actually in the Journal which got so much attention online that it became a piece in the physical paper. and it was called The Rise of the Atheist, something along those lines. It got quite a bit of press. I'm actually running out of things to say, which is
I'm just waiting.
quite rare. Oh, we're good?
Yeah.
Okay.
I just won't load, so I don't know.
You might want to actually tell them what the website address is.
Oh, sure. www.centerforinquiry.net/Ontario is the website for CFI Ontario. It's also listed in the brochure if you want to pick those up on the table. And now I think we're good to go. Okay, thanks for your attention.
It's very rare for me to actually have difficulties with my computer in interfacing with devices. I'm known as the gadget girl around the department. For example, you can tell that this is sort of part of my priority set by the fact that I dress my iPhone better than I dress my person. It has an Italian hand-stitched leather case, and it's hacked, by the way. It works on a Canadian network. At any rate, what I'm here to do today, tonight, I tend to move around a bit, which is why I'm doing the dorky thing of holding this thing up to my mouth. So with any luck, you can actually hear me all right. Is that sort of good, roughly speaking? Can people who are aged at the back hear me all right? Somebody with grey hair? Can you hear me? Cool. No, I'm just not meaning to be discriminatory with the remarks, simply that my own father is almost 70 and his hearing is decreasing as he gets older, and so I just have a little bit of a sensitivity about that, and that was all I was trying to express. So what I thought I would do in this talk is to try to, over the period of roughly, say, 3/4 of an hour or so, is give you a story. And what the story is going to tell you about is about string theory. But I will need to spend probably more than half of the description just sort of talking about background, because there's a lot of physics that came before string theory, something that I work on and other people also are quite excited about, but that it provides an awful lot of intellectual horsepower and structure. So it'll seem like for the first part of my talk that I'm not really talking about the subject of the presentation, but in fact I am. I'll just be building up sort of structures so that you'll be able to see the presentation of string theory, which will make an appearance roughly about Act 3 of a 4-act play. And you will see just how marvelous it is and what problems it solves. And I hope that by the end there will be plenty of questions. I am even willing, of course there will be a Q&A of however long you can stick it at the end. I can go on about string theory forever. I am a professor after all, so I have no shortage of hot air. Sorry, I didn't mean to tar all my colleagues with one brush by making a silly comment. But anyhow, what I thought I would do is, in the beginning, just introduce a little bit about your speaker and what the hell is the subject of this talk, and some aspects of physics, and then I'll talk a little bit about modern particle physics, particles and forces, the new machine called the Large Hadron Collider, which is about to start up this year and which we're all very excited to see the results from, and how that motivates perhaps a unification of forces and particles. And then I'll bring together what we know about cosmology and talk about some string theory aspects. I'll then even change into fourth gear and be able to talk a little bit about some of what you might call the sexy topics, like extra dimensions and supersymmetry and brains and all those sorts of wonderful things. So I am willing to entertain questions during the talk, but I would ask people who wish to ask questions during the talk, would you please ask a question that's useful to everyone in the room and not just to yourself? So modulo that constraint, I'm happy to take questions during. And I, of course, reserve the right to postpone the answering of the question until the Q&A. But if it turns out to be a useful question, then I'll dwell on it a little. So, sort of Act 1 of the 4-act play. Sorry. This is an old joke for those who know me in the string theory community, so I was able to use this in my conference presentations about 4 years ago and get away with it, but it just, it takes a little, anyway. So those of you who were expecting to come and hear a talk by that other Amanda Peet, the babe, who appears in Hollywood movies and stuff, I'm very sorry to disappoint you. This Amanda Peet is the one who's giving the talk, not the Hollywood actress. I have actually had people challenge me when I ring up to make a restaurant reservation and say, "Oh, you must be kidding. What are you trying to pull? I don't think you're Amanda Peet, the Hollywood actress." And I'm not. No, I'm not. I'm Amanda Peet, the physics professor. So anyway, let's just say we didn't choose that restaurant. So I just wanted to rip off the title of a Stephen Hawking book and just give you a very little introduction to me, just to help to set the scene and get you comfortable with listening to this particular person. I actually happen to have been born in a small island nation in the Northern Hemisphere, in Great Britain. Whether it's great or not is, up for a debate. Another question I have to ask about that is that when was the wealth common? Anyway, and then, well, as you can see, at the age of a few months old, I was transported to a small Pacific island nation in the South Pacific Ocean called New Zealand, and I grew up there and went to school there and had a very good undergraduate education there. And then, for some reason, Stanford let me into their graduate program, and so I went off to America, and about all I knew about the US at that point was that they had highway cops called chips, and that they rode motorcycles and pulled people over and did stuff like that. That's about all I knew about the whole United States before I took off. And then somehow I ended up doing a postdoc in Princeton and ping-ponged back into California and did a postdoc at Santa Barbara. Oh, I've been the brownest and the fair-hairedest when I was at Santa Barbara my whole life. Lots of sunshine. And then somehow I managed to come back to here, and so I'm in Toronto. I have been since 2000. And I would like you to know that I'm a member of a group. So I'm not the only string theorist in Toronto. I'm certainly not the only one in Canada. And there are colleagues of mine at the University of Toronto who are also really excellent physicists. Not meaning to make any statements about my own abilities, but I'm just one of a team. So I'm the one in my group who tends to be most interested in reaching out to the public and doing these sorts of talks. So you didn't see Kentaro Hori on the string theory documentary by Brian Greene, and you didn't see other Canadian string theorists represented. I was the only one there at a Canadian institution represented on the program. Yay, go Canada! And it takes a Kiwi to do it, huh? Well, anyway, so no worries. But anyway, it's been a lot of fun, and by the way, you'll notice that unlike any good physicist, I haven't put the actual graph of the units along the bottom, so I'm not telling you how old I am. However, I will admit that I was born around the same time as string theory was, which was in the late 60s. So at any rate, when I'm talking about my colleagues and I, the team members in our group that we're talking about, what motivates us? What is the reason why we're interested in studying the fundamentals of particles and forces all the way from the subatomic to the edges of the cosmos? I mean, what makes us tick? Well, physicists generally come in a couple of flavors. We call ourselves theorists or experimentalists, depending on whether we prefer to wrangle math or apparatus. So I happen to be disastrous around experimental apparatus, so that's sort of like one of the reasons why I became a theorist. So I wrangle math equations and stuff, but it's not really that different in spirit from what my experimental colleagues do. So what we're interested in doing, for a physicist, what's really interesting is to pick a particular distance scale. So to say, well, I'm interested in physics on a scale of kilometers. For example, that would be a distance scale relevant to weather. I'm interested in predicting what the forecast is going to be for tomorrow. I don't really need to know about the subatomic structure of atoms or molecules in order to be able to do a pretty good job with predicting the weather. I mean, it's sort of icing on the cake, but what I need to know is about the physics of fluids and how air masses move and things like that in order to be able to understand weather. So what a physicist will often do is characterize what they're talking about by saying, how big is it? So I'm saying, if I'm interested in for example, the atom, then if I look at the size of an atom, then it's about a tenth of a billionth of a meter across. Now, physicists tend to run into problems, and I'm running into this problem already here, which is in characterizing how big is something. The trouble is that we're dealing with length scales that vary very widely across a lot of different stories. So, for example, if I'm a human being, I have a size of approximately a meter. And if I use my eyes and my fingers and so forth, I can look down to about scales of millimeters. But if I want to look down at much shorter distance scales, if I want to zoom in many more times to get a magnification on what I'm looking at, my own eyes are no longer very useful for that, and I'd have to switch to a microscope. I look to something that's got magnifying power. Similarly, if I wanted, instead of to look at the microscopic world, but instead I was interested in studying the macroscopic world, I wanted to look out not just across the Earth, millions of meters, but I wanted to look out billions and even further into the rest of the solar system, the rest of the Milky Way galaxy. I might even be interested in what happens in the whole freaking universe. That's a lot of stuff. And so what am I going to do in order to describe which length scale I'm talking about? And physicists use this notation, these math symbols on a page. And when I say that the size of an atom is about 10 to the minus 10 meters across, all that means, what the minus 10 means, is that I would, if I had suppose I had an operation that I could do when I clicked my fingers, I could zoom in by a factor of 10. So what 10 to the minus 10 meters really means is that 10 times I said zoom in by a factor of 10. So I zoomed in once, and I was looking at it, instead of a length scale of a meter, I was looking at a length scale of 10 centimeters. Then I zoomed in another time, and I'd be looking at a length scale of a centimeter. If I zoomed in another time, I would be looking at a length scale of a millimeter, and so forth. So the question is, how many times did I have to zoom in from my scale, my size of my human being, about a meter or so, in order to look at the item I'm talking about? So if you see a physicist say, well, the size of an atomic nucleus is about 10 to the minus 15 meters, all that mathematical story means is that if I started out with about the size of a human, I would have to zoom in by a factor of 10 about 15 times to be able to see that tiny distance scale. At any rate, the big message from asking a physicist, what do you do all day, or what do you think about all night, a physicist will say, well, I'm interested in systems that have to do with this length scale. And so we have a whole continuum of people who sit in the department, some of whom think about very, very short distance scales. So for example, I'm one of the people who thinks about the structure of matter on the very tiniest distance scales we can possibly imagine, which is, let's just say, about a billionth millionth of a centimeter, just unimaginably tiny distances. We say that that's 10 to the minus 33 centimeters because it just means that if we started off with human size, we'd have to zoom in by a factor of 10, 33 times to get to that size. So, on the other hand, I might be interested, instead of studying the microscopic world, very tiny distances that have to do with the subatomic structure of atoms, or if we went down even smaller distances to the structure of the nucleus, or even tinier distances than that to talk about subatomic particles. But I might say to myself, well, I'm actually also interested in the physics of the big. So I'm not interested in that which I can access with a microscope. I'm interested in what I can access with a telescope. So then you start talking about zooming out. For example, if I would like to look at something that is, say, 1,000,000 kilometers wide, then I would have to zoom out quite a few times from this human scale to be able to fit all of that in my telescope. So physicists say to themselves, well, I'm interested in studying some physics, some stuff, like it's the physics of the weather, or it's the physics of subatomic particles, or it's the physics of galaxies. You ask a physicist what they study, what they'll all come back and say to you is, well, the size of my system that I'm studying is about this big, and so I can go and do blah, 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 blah. And they can give courses and everything about what happens at that distance scale. But what I'm trying to get across is that physicists are interested in understanding the basics, how things work, at distances that range over 60 orders of magnitude. We're interested in studying physics all the way from the very smallest subatomic distance scales, 10 to the minus 33 centimeters, or that just means a billionth of a billionth of a billionth of a billionth of a millionth, or something really, really weeny. All the way from there, through the scales that we're familiar with, to the micro, to the millimeters, to the kilometers, out to the galaxies, and out to the very edges of the universe. So if you like, physicists are these extremely arrogant creatures who are interested in understanding all the forces and all the subatomic Legos that make up a universe. I prefer the word Legos than subatomic particles or fundamental particles or something, just because Lego was my favorite toy when I was a child. And I sort of think, well, once you start out with those basic bricks, building blocks, you can make a lot of things, especially if you've got a good imagination. So, likewise, physicists are interested in saying, well, once I've figured out how big my system is, then let me sort of poke it, see what happens. After all, if we want a really good job description of what a physicist does, it's to look at a system, poke it, see what happens. Do some measuring, do some modeling using math, do some more measuring, do some more modeling, and then come up with an explanation of how things work. So we're interested in sort of having the arrogant point of view that we'd like to understand, say, the force of gravity, and that's my favorite force, so of course I would pick that as my example. I just love gravity, it's my favorite force in the whole universe. And I would like to understand gravity all the way from those very shortest subatomic, teeny weeny distance scales, all the way through the physics of humans and planets and galaxies out to the very edges of the known universe, which is at about 10 to the plus 28 centimeters. And what that distance scale means is that if I took myself and then zoomed out by a factor of 10, and I did that 28 times, that's how big I would have a distance. I mean, that's a really freaking huge distance scale. I don't know how many of you have heard about, just to get these sizes in perspective, there's a set of crazy, elderly, by now, British comics who, you know, formed this group called Monty Python or something, and they said that there were 3 sizes of things. And this sort of helps to get this across, I think. There was wee, not so wee, and friggin' huge! So what we're talking about here is I'm the not so wee, I'm just regular, ordinary size. The subatomic particles that I want to study, you know, is in particle physics, are the really wee, and then the stuff I want to study to do with the whole universe is the friggin' huge! So I want to go from all the way from the really wee to the not so wee to the friggin' huge. And I want to be able to understand the laws of physics, the laws of, say, forces between things, or how much gravity pulls something. I want to understand the structure of matter and of force, all the way from the subatomic, the really wee, to the friggin' huge. I want to cover the whole thing. And as you can imagine, coming up with a thing that can describe this can be a wee bit of a challenge. So that's one reason why there's still controversy, why there is research happening in the field, why people are arguing about things. Sometimes they argue about it inside the walls of universities, sometimes they argue about it in the popular media, and sometimes even on TV. But one thing that tells you is that there's a lot of activity, a lot of thought going into it. One of the things that I wanted to get across in this talk was to focus a little bit on the physics of the very small, partly because this may not be a world that's particularly familiar to us. I mean, after all, we're used to the physics of dogs and balls and hockey pucks and cars and, you know, maybe a little bit about the weather systems that cover thousands of kilometers or something, but most of our life takes place within a pretty restricted context. But what I'd like to point out, and mostly these slides up here, by the way, are notes for me to remember what to say. One shouldn't expect, if one were an audience member, to instantly look at these things and instantly understand what they mean. It's just sort of a reminder for what I meant to say. But I'm not sure how easy it is to see this from various points in the room. But what I was trying to get across with this little thing here is to talk about the subatomic. So what would the physics look like if instead of being humans, you were subatomic particles? I mean, suppose that, for example, this beautiful woman here was an electron. Or suppose that this chap over here was, I don't know, a neutrino particle. Would anything about the laws of nature or the way things are be very different at short distance scales? And the answer is surprisingly yes. And the physics of the micro world, the physics of really wee things, the physics of atoms and the nucleus that is inside of atoms and the electrons that whiz around the nucleus, and inside the nucleus, by the way, did you ever wonder why an atomic nucleus doesn't explode? I mean, I know that sounds like a kind of a weird question, but you probably learned when you were in school that atoms have inside them a hard little compact nucleus in the middle that's got positive protons inside it and some neutrons which don't have any charge. And those are all clumped together really, really in a compact little thingy. And that's about a millionth of a billionth of a meter across. So it's really weak. But inside that little nucleus, and there's a bunch of electrons going around the outside, but let's ignore those for a minute. But suppose that you focused on the atomic nucleus, and this is represented a bit clumsily in this little picture here. But as you know, if you take a positive charge in a proton and another positive charge, they repel each other. So you learned that like charges repel, but opposite charges attract. You know, we often apply that, we pervert that law to say something about the laws of human attraction. At any rate, the protons inside the nucleus would like to push each other out of the way. They repel each other because they both have positive charge. And so according to electric force, the protons should go apart from each other. The nucleus should explode. But why don't they? Well, the neutrons don't do anything magic. I mean, after all, they don't feel the push or the pull of electric force because they don't have any charge. So what must be happening is inside the nucleus, there's a magic extra special force